sometimes there's like a physics problem that happens in real life, and I'm compelled to analyze it, and that's what we're going to do today. And really, my whole goal here is to model this. Let me go ahead and show it to you. Now, I hope I don't get in trouble for this. It's online, so here we go. So this is from the San Francisco versus Buffalo football game. It snowed a lot. They get a lot of snow in Buffalo, and San Francisco's kicking a field goal, and someone says, hey, I could stop that from the stands by throwing a snowball at it. They missed. But let me just show you really quick. I think this will be okay. So here's a little clip of it right here. We can watch that. Kick the field goal. You can't really see the snowball, but boom, we almost, it's kind of funny. It's kind of an interesting idea that someone would even try that. So would it work? But more importantly, what would it look like in Python? And how would you model that? So we're going to build a football, part of the football goal, and the football and the snowball, and we're going to make them collide, and it's going to be great. But let's first talk about momentum, right? So if suppose, and I have some details up here because I won't forget, size of the goal. I picked some velocities and mass of the ball and velocity and the mass of the snowball. So of course, if I have two objects, let's call this A, let's call this B, and they collide, and maybe you've seen this before, and that's fine. Well, during that collision, then there is a force that A exerts on B, and there's an equal and opposite force that B exerts on A. That's Newton's third law. So I can write this like that, F A, this is A on B, and this would be F B on A. And you can model this in a lot of different ways, but I'm just going to say there is an interaction. And then this has some momentum. We'll call that PA1 and PB1. So the net force on object B is FA on B, and that's going to be the change in momentum PB1 with respect to time. And then you could do the same thing for the other object, FB on A. That's going to be equal to the change in momentum of A. That's just change in momentum of A. I'm kind of sloppy right now. Delta PA with respect to T. But this force is the opposite of that, so this has to be the opposite of that. So what you get is the change in momentum for B is equal to negative the change in momentum of A, or the total change is 0. Or you could say P1 equals P2. So this is the momentum before the collision. That's the momentum after the collision. Conservation of momentum. Now, there's really two things that can make this true. Number one, if there's any other extra forces on our colliding objects, then it's not true, right? Because the net force is not the change in momentum if you have an extra force in there. So that has to be the only force. Or the collision takes such a short amount of time that the changes in momentum due to an external force are just small and you can ignore them. And that's what we have here. So if I have a football and then a snowball collides with it, and that collision takes a very short amount of time, the gravitational force and the air resistance force just don't change it that much, so we can use conservation momentum in that case. Again, this is not the main point of the video. It's to build this whole thing in Python. So let's just say that I have a football, because we want to estimate the deviation. So here's my, let's call it momentum of the football 1 before the collision. And then I have a snowball like this, momentum of the snowball before the collision. And then after the collision, they have some new momentum. I don't know, maybe it'd be up, I guess. Doesn't really matter. P, let's call this MF plus MS V2. So that's the total mass. They stick together. So that's the total mass times the new velocity. And we could find that new velocity, V2, is going to be equal to PF1 plus PF2, all that over the total mass, MF plus M. No, this is PS1, MS. And so that's what we're going to do. So if I know the velocities right before they collide, I can just calculate the final velocity afterwards. And that's what I'm going to do. So I'm going to take my football, and I'm going to, right when they collide, then I'll just calculate the new velocity and make the things move off together like that. That's my goal. Okay. So that's the conservation momentum part. Now, we do have a bunch of model building here, right? Because suppose if you look at that picture, you have a field goal and the ball's coming this way and the other one's coming from some weird angle. How do I make them hit? I want them to hit. I can't really calculate when and where to throw it. So what I'm going to do something I'm going to explain to you what I'm going to do. So I'm going to build, let's just build the field goal first and kick the football. And then we'll deal with the snowball. I'll come back to the board and we'll deal with the snowball. So here's my field goal in terms of meters. It has a 3.1 meter tall post. The crossbar is 5.6 meters. And I think I got 10 meters for the height of those, but it doesn't really matter too much. And then in this case, it was a 33-yard field goal, so that would be 30 meters. So it's 30 meters where the ball starts away. So I'm going to put my field goal in the the XZ plane, 10 meters in the X direction, so it's not all in the center. I don't want to put that at the origin. And then we'll start building from there. So let's go ahead and start building stuff in Web VPython. Let me get off this page so it doesn't, I'm just afraid that's like, I'm going to get a strike or something like that. Okay, so I'm in Web VPython. We're going to use Web VPython to draw. We're drawing stuff, right? It's going to be fun. It's art time. Okay, so let me just enter in, I'm going to, of course, need G. So I don't know why I just need to put that in there now. Negative 9.8. 0. Okay. The next thing I want to do is to make this vertical bar right there. Okay. And I don't need to group them. I don't even need to give them a name because I'm not going to use anything with them. But let's call this the post. Post is going to be a cylinder. And it's going to, remember the cylinder object, you define the starting point and then the axis to the other point. So in this case, I'm going to put the starting point at the position of vector, is this big enough? I think that's big enough. 10, 0, 0. So it's 10 on the x-axis. And then the axis is going to be going up in the y direction. So that's going to be vector 0, what did I say, 3.1, 0. Now I'd need to give it a radius. Radius is going to be, I think it's like, I want to make sure you can see it. So let's say a radius of, I'm going to try 6 centimeters. It has an actual radius, but, and then I'm going to give it a color equals color.yellow because, you know, it's a goalpost. And let's just run it. It's always best just to run this thing one time. Okay, there's my post. Now I'm going to make the crossbar. Let's call it CB. It's also a cylinder. Now, let's just say, I'm going to do this. The width of the bar is 5.6. I need to go over half that and then go across that. So it's kind of complicated there. So let's give it a position on one end. So the position is going to be the vector. In the x direction, it's 10. It's the same x value, but now I need to move in the negative z direction. So the y value is going to be 0, right? No, the y value is going to be equal to 3.1 because it has to go up. And then the z value is negative wb over 2. For the axis, it's going to be going in the z direction, so it's vector 0, 0, wb over wb. And then the radius is the same, 0.06, color equals color.yellow. Run it. So you see how we're building one piece at a time, right? You don't want to do it all at once. Now I can build the upper post. So let's call up 1. It's also a cylinder. Its position is going to be the left end of that thing, which is the same as CB. So I'm just going to say the position is cb.pos. It's the same thing, right? Now I just need to go up. So axis is going to be equal to vector 0, 10, 0, radius equals 0, what about 0.06, color equals color.yellow. Run it. There we go. Look, it's starting to look like a goalpost, right? It's kind of cool. Okay, now I'm going to do up 2. It's also a cylinder. Position is going to be the other side. So let's just say, let's do cb.pos plus cb.axis, right? That gets me to the other side of that crossbar. I could type it in normally too. And then the axis is the same, vector 0, 10, 0, radius, oh, I hit that. Radius equals 0.06, color equals color dot yellow. Run it. There you go. You see? It's kind of cool, right? Now, I do want to put in a ground. Now, I always have problems with boxes because the ground is a box, and the location of the box is the center. So if it has some thickness, you need to take that into account. I'm not really going to care. I'm just going to make it really thin and not even worry about it. So let's put, say the ground is a box. It's good to give it a name, even though you could just say box, because if I want to move it, I could just move the box. I don't have to redo it. Let's say the position is at the origin. And then the size is going to be equal to, okay, so I need it kind of big, right? Because I want the football kick to be, or at least close to it. So let's say that would be 30 meters to the left, 30 meters to the right, would be 60. Let's try that. Vector 60, and then the width, let's say is 30, and then the height is going to be, oh, no, I want this to be the height. Let's say 0.5, and then the width to be 30. And then we'll put this as color equals color dot green, because it's not Boise State, right? It's a football game. Let's run that. Okay, I think I'm pretty happy with that. I think I'm going to make it a little thinner, just because I don't need that thickness. Let's make this 15, and it'll make it look a little bit better. Yeah, let's make it thinner, 10. I think my goalposts need to be a little bit thicker in radius, right? I just want them to show up a little bit better. So let's put this at 9. Let's put that one, just that one at 9. See how that looks. Yeah, that looks better. Okay, let's put those at 9. Because 9 is just an upside down 6, right? That's why I picked it. Okay. Art. Okay, there's our field. Good job. Save it. Okay. Now I'm going to put my football there, and I'm going to kick it. And I want to make sure it goes to the goalpost and stuff like that. So I just need to pick some values. I'm ignoring air resistance. You can add that in later if you want to, but I'm just trying to get a rough animation going here. So let's just call it a ball. It's a sphere. Its position is going to be equal to, so I want it to be 30 meters away from the field goal, so it's going to have an x position of -20, right? Because the goal is at 10. So the vector -20, 0, 0. Now you could give it some z direction if you wanted to. That would be kind of fun, but I'm just going to say they're kicking right from the middle. Again, you can change that if you want to. Let's just do that. And then the radius, I definitely want this ball to be visible. I actually made, in a previous calculation, I made a 3-dimensional football, but you can't see any dimensions because it's too small, so I'm not even going to worry about that. Let's say the radius is 0.05, color equals color dot magenta, and then make trail equals true, because we want to see that. Real footballs don't do that, but that's okay. Let's just run it and see what that looks like. Can I even see that? No, I can't see it. Did I get an error? Where's my ball? Oh, I think it's underneath the thing. Let's just raise it up 1 meter. Is that it right there? It's just tiny. Okay, so let's make it a radius of 0.1. Yeah, there it is. That's tiny. So that's too tiny. Let's say 0.2, and let's put this back at 0. Oh, see, it's below the thing. So 0.5, raise it up. Okay, that's good enough. Not realistic, but good enough. Okay, so I have the mass. Let's say MF is 0. That's the mass of the football, 0.4. And I'm going to go ahead and give it an initial momentum. Ball.p equals MF times vector. Now I'm going to shoot it at let's say a 30-degree angle. I'm just picking a 30-degree angle. So 30 meters per second times cosine of, let's say, theta b is 30 times pi divided by 180. And that way I don't have to convert over here. So cosine theta b, 30 times sine of theta b, 0. Okay, so now I have an initial momentum. I have the gravitational force. So I have enough to actually kick the ball. T equals 0, dt equals 0.01. I'm running out of room right there. So while t is less than, let's just run this for 2 seconds. I don't even know. Rate 100. That makes it run in real time. And now I need to calculate the force on the ball. But I don't need to because it doesn't change. So I'm just going to update the momentum of the ball. Ball.p, can't see that. Ball.p equals ball.p. And this is the momentum principle to update that. Times the gravitational force, which is mf times g times dt. So that updates the momentum. I feel like that's a little too small. Okay. And now I need to update the position. Ball.pos, ball.pos plus ball.p times dt divided by mf, and then update time. T equals t plus dt. Let's run this thing and see if we get a field goal. That's a little high, I think. Okay, so let's aim that at maybe 20 degrees. I don't know too much about kicking footballs. I'm just trying to go by what looks right. Oh, that's too low. That's not bad. Let's do 25. I got this velocity by just looking at how far away they were and how long it took to get there. That's pretty good. Okay, so now what I want to do, I want to pick the collision point. So I'm just going to run this for a certain amount of time. Let's just change this time to 1 second and see what happens. 1 second. I want it to stop before it gets to the goalpost. Because if you hit the ball with the snowball after it hits the goalpost, there's no point, right? So that's pretty good, right? That's where my ball is going to be. That's good. 1 second, that's where I want the collision to happen. Now, let's just for fun, I'm going to angle it just a tiny little bit in the z direction. So let's just give it a z component, not much. I'm just going to pick a value. It's going to change everything a little bit, but that's fine. Ball.p, let's give it a z velocity of, let's say, 3. Let's just see what happens there. Oh, I missed. Okay, let's not do that. Let's do 1. You can play around with, and I did change the total velocity doing that, but okay, good. So I have here the place where I want the collision to happen. So let's do this. Let's just print. Print ball.pos. I want to print the location of that ball because I'm going to use that ball to then make sure my snowball hits that point. But I need to know what that point is. And yes, you could calculate that beforehand. It's just normal projectile motion. But I don't want to do that. So if I run this, okay, there's my final position. I'm going to copy that. This is the cheating. I know it's cheating. Don't worry. Cheating's okay sometimes. And up here, I'm going to say target, that's my target location, is vector, that. Now what am I going to do? Okay, let's go to the board because I want to explain to you my little trickery here. I don't need that anymore. Okay, erasing this stuff. I do need that equation right there, so I'm going to put that V2 is going to be PF1 plus PS1 over MS plus MF. I don't need really, I'm not going to forget that. Okay, so here's my goalpost. Here's my football. And there's the target location. Now what I want is to imagine that my snowball did this. And I want to land at that same spot right there. So if I know the final velocity, we'll call this VS snowball 2. What I could then do, since there's no air resistance, and I can use the kinematic equations in reverse. What I'm going to do is to give it the negative of this velocity and start right here and then let it travel backward for t equals 1 second, and then print that location and print that velocity. And then I can run it back the other way, because in projectile motion, it doesn't matter which way you go in time. That is a trick, right? But then I know that if I start right there with that final velocity and position that I print, it's going to end up over here. Does that make sense? So let's do that. I need to pick my velocities, so I'll do that. Okay, going back to the computer. So I'm already there. What I'm going to do now is to start back at time t equals 0 and just go backwards. So t equals 0. I'm starting over. Now I'm going to pick my velocity of the snowball. Let's say it's vs0. Vs is fine, because I'm going to change it. So I want it to have a velocity of 20 meters per second. And then I want it to be coming at the snowball at a 30-degree angle. So this is going to be vector, let's call this theta s is 30 times pi over 180. And that's in the xz plane. So this is going to be vector 20 times cosine, right? 20 times cosine of theta s. The y component, I'm just going to pick. I'm just going to pick a value. I want it to have some negative y value. So let's say -5, 4. I'm picking something. And then, oh, this is negative. No, wait, I'm going in the positive direction. I'm going backwards, so that's positive. And that's positive. And then the z component, I want it to go in the negative z direction. So it's going to be -20 times sine of theta s. So I have an initial velocity. Now let's give my snowball. Let's make my snowball. I'll put it up here. I do need to move it. That's fine. Snow, it's a sphere. POS is my target, so I need to put it after this. Snow equals sphere. POS equals target. That's where it's going to start. Radius is going to be equal to 0.2, same thing. And then color is color.cyan. It's a snowball. I could leave it as white. I could leave off the color and it'd be white. Make trail equals true. Now I need the mass too. I don't really need that. MS is 0.13. So what it is, I picked a reasonable size of a snowball and reasonable density and all that stuff. So I have that. Let's go ahead and write this as a momentum. Snow.p is ms times vs. Now I can just make my motion go normally. So while t is less than 1, the same time as before, right? Because I want those two things to start at the same time. Even if they don't, that doesn't really matter. I'm really looking at that collision. Rate 100 we don't really need. So then I'm just going to calculate the momentum. Snow.p equals snow.p plus ms times g times dt. That's the force. Snow.pos, snow.pos plus snow.p times dt divided by ms, and then update time. T equals t plus dt. And here you see I had to reset my time equal to 0 so that I could get to 1 second. And then once we get done, I'm going to print, let's say, snow.pos, snow.pos. And then I need the snow momentum, I guess. I can just say snow momentum. Print snow p equals snow.p. So there's that part. It hit my target, and then my target went off. Like that. See, so that, now I just want to reverse that snowball right there. And I can do that because I have these things. So let's just copy that and go over here to edit. And then I'm going to paste those up here. So now I can do this. Oops. So it's a comment, because that's not the right code. So I have the snow, I have the target position. I'm actually going to move the target position, right? I'm actually just going to put the position right here. I'm going to copy that and put that as the position. That's it. So now I know where it's going to start. Now for the momentum, I'm going to say down here, snow.p equals this stuff. I don't even care about the mass. I've already got that into account. Negative that, though. Negative that vector. So now I have it. Now I don't need this stuff. Let's just comment that out. And then go back up here. All I need to do is update the momentum of the snowball. Snow.p equals snow.p plus ms times g times dt. And then update the snowball's position. Snow.pos is snow.pos plus snow.p times dt divided by ms. And that should be it. But that'll just show the two balls colliding, and then I'll need to handle collisions after that. But let's just do this, see if this works. If it works, that's pretty cool, right? There they go. Boom! Okay, so now I want to model what happens afterwards. So they're going to have the same motion. So let's just run it for another half a second or something like that. And so what I'm going to do down here is to calculate the new velocity. I'm just going to delete this stuff. You don't need that. I'll leave it there just in case you want it. So after that time, I'm going to calculate the new velocity. I'm going to say V2 is snow.p plus ball.p divided by ms plus mf. So that's the final velocity at the end of that collision. So I'm using their velocities right before the collision to calculate the new velocity V2. And then I can move the objects. So let's just run it for another time while t is less than 1.5, another half a second. Number 1 over 8/100. Now I can just update the velocity. I don't need to update momentum. So I'm going to say, I'm going to update the momentum though. No, I do need to change the velocity. So I have that velocity, it is a vector. So let's just change that velocity. So V2 is equal to V2 plus g times dt, and then I can update the positions. So snow.pos equals snow.pos plus v2 times dt, and then the football too, so ball.pos is equal to snow.pos. It's the same thing. And then update time. T equals t plus dt. I think that's it. There they're going to collide. Oh, that didn't work. Let's print V2. Maybe that doesn't seem right. It should be right. Oh, that's because it's down here. I've recalculated that. That's why. Yeah. I gave it the initial momentum in the other direction. Oops. What happened? Oh, it did. Okay, it worked. There we go. And it still made the field goal, you see. And you can see the deflection right there. Not a huge deflection. But you can try a bunch of things from here. You could say, okay, now what happens if if it's an inelastic collision? What happens if it bounces off? Well, if it's a hard snowball, then the calculations get a lot more complicated, but you can indeed do it. There's other ways to do it too. You could try, what if he throws faster? What if there's two snowballs that hit? What if all these situations you can do? But really, the thing is you can make this 3D representation right here, which I love. And that's what makes me kind of happy. So there you go. Still field goal, 3 points for San Francisco. I think they lost that game though. Okay, so I'll give you this code down below in case you don't want to rebuild your own field goal. You can just use my code. But that's that. Hope you enjoyed it. I had a great time. Real world physics right in your TV and on the computer.